All right, recording now. Fatigue 1, question 1. The fatigue behavior of a specimen under alternating stress condition with zero mean stress. Remember, alternating stress condition and zero mean stress means fully reversed loading. That's what we are talking about. And so that thing that we find is also the endurance limit. Is given by this expression here, sigma r to the power of a times nf equals k, capital K, where sigma r is the range of stress, nf is the number of cycles to failure, and k and a, so k is this number here, and a is the exponent, are the material properties, material constants. It is known that for 10 million cycles, it is known that this specimen lasts 10 million cycles, sorry, 1 million cycles, when the stress range is 300 megapascal, and it lasts 100 million cycles, when the stress range is 200 megapascals. We need to calculate the constants K and A, and also the life of the specimen when is subjected to a stress range of 100 megapascals. So let me copy this information first. So this is question fatigue 1. Question 1. And so what we know is that the fatigue model is corresponding to this equation, sigma r to the power of a. So sigma r to the power of a times nf equals capital K. And we also know two of these points. Remember, this is an exponential equation, but in log-log scale, in a log-log plot, the exponential equation is just the equation of a straight line. So that means we only need two experiments, which we have, in order to interpolate and extrapolate the behavior at any stress range or at any number of cycles to failure. Okay, so 1 million. So for a stress range of 300 megapascal, our number of cycles to fatigue is 1 million, 10 to the power of 6 cycles. And for a stress range of 200 megapascals, our number of cycles to fatigue is 100 million. So 10 to the power of 8 cycles. And we want to find K and A. So how much is K, how much is A? Basically the parameters of the model, of the fatigue model. And what is the life of the specimen? So NF such that the stress range is 100 megapascal. So this is what I have on, basically. That's it. So this is my model. This is fatigue model. These are the model parameters. And that's it. So how do we find this? I don't know why it's taking a bit to hold. Let me check. No, it takes a while. So let me disconnect this again. Just a second, please. I don't know why I have some extreme lagging. Let's try this. Yeah, much better. Okay, so let's start by, so we have these two conditions here, condition 1, condition 2. So let's use them in the model. So let's substitute conditions 1, 2 in the model. And so this gives us a system of two equations, 300 to the power of a times 10 to the power of 6 equals k, and 200 to the power of a times 10 to the power of 8 equals k. You agree with me? That's very easy. So this is what we know effectively. So how do we solve this? There are two ways of solving this by hand. Well, you can plug this in Mathematica and it will give you a solution, but I want you to write at least 1 or 2 steps into the solutions. Because otherwise it looks like you have copied it off somewhere. So the first way of addressing this is pass everything into logs. So if you do the log of the left-hand side equals the log of the right-hand side, and this log is the natural log, okay? You get this, okay? And then using the logarithmic properties, the properties of the logarithms, you know that the logarithm of a sum, the logarithm of a multiplication is the sum of the logarithms, and the logarithm of an exponential is the multiplication of the exponent times the logarithm of the base. Basically, what I'm saying is that this looks like a log of 300 plus log of 10 to the power of 6 equals log of k. That's equation 1. Equation 2 is a log 200 plus log 10 to the power of 8 equals log of k. And from here, you can just find a and k. You can find a by substituting so on and so forth. So you can find how much is a, how much is k. The other way of doing this is other way. Divide equation 1 by equation 2, 1 over 2. Then you get an equation that looks like 300 divided by 200, it's 3 halves of a to the power of a times 10 to the power of minus 2 equals 1. And so from this, you get that 3 divided by 2 to the power of a is 1 over 10 to the power of 2, 10 to the power of minus 2, which is 10 to the power of 2, basically. Let's put this here, 10 to the power of 2. And so finally, a equals the log in base 3 halves of 10 to the power of 100. Okay, this is the other way. So in this case, you can find a. Once you have found a, you go back into one of those equations and find k. Now, if you don't know how to find this thing, which is a bit complicated, the log in base 1.5, well, in that case, you can remember that log in base b, let's say log in base a of x equals log in base b of x divided by log in base b of A. And so let's make this the actual log. So you can use the natural log in this case. So log of, in this case, that's the log 3/2 in this example here of A is equal to log of A divided by log of 3. Okay. And this gives, and so you can find A, and this is equal to A. Sorry, this is 100. 100, this is 100, and this is equal to A. Okay. Any questions? We have now found what power number is that next to the 3/2? A, just A. Very good. All right, that's it. That's it. We found A and K. Well, did we? Let's see that we found them. It's just a note of calculation. So A is 11.357. 11.357. And K is 1.356 times 10 to the power of 34. Wow, it's a huge number. Okay, so these are the first two answers that we wanted. And the last answer says find how many numbers of cycles for 100 megapascal. I mean, this is very easy now because we have this model. We know A and K. We know that this must be 100, so we can just find K. Sorry, NF. So NF at sigma range equals 100 is equal to, so remember the equation is K over sigma R to the power of A, which is equal to K over 100 to the power of A, which is equal to K and A. These are numbers that we just found. Let me check the solution. That should be 262 times 10 to the power of 9 cycles. 262 times 10 to the power of 9 cycles, which is a lot of cycles. A lot of cycles. Yeah, this is what we wanted. Done. As you can see, it's very easy. Not very complicated at all. Everything is just to understand what's going on and what are the quantities that you are looking at. Okay, so let's do, if you don't have any questions, I'll go through question 3. Of course, I will not give you any breaks, okay, because if we finish in 1 hour, that's it, that's done. Do we take into account the units mega? Well, that's up to you, okay, because these A and K will have different units and will be different numbers depending on what you want to put here and here. So these A and K are just empirical numbers that don't mean anything. Those are just the two numbers that make it work. Okay, experimentally. That's the empirical relationship that you have. So this doesn't come from any elasticity theory, really. So this is just an experiment. Remember Waller's curve, Waller's experiment. Just say, okay, let's see how much time, how many cycles it takes until it breaks. So you just fit a curve. That's what you're doing. So if you use megapascal and cycles, that's fine. You get some numbers here that will work with megapascals and cycles. So as long as you are consistent every time, you always use megapascals, you always use cycles, you will be 100% fine. If you start mixing and matching units, you might be in trouble. All right, so let's do question 3. A mild steel shaft has a pulley mounted at each end and is supported symmetrically in between two bearing housings. When rotating under load, the shaft will be subjected to a cyclical bending moment of plus or minus 1.2 kilonewton meters. F is saying, when I put it in the calculator, it's 10 to the power of 11 cycles, not 10 to the power of 9. Is it 2.62, 10 to the power of 11? Because we are saying the same thing. Mine is 262. Okay. No, you're not done. It happens. It's fine. Don't worry. It's fine. 1.2 kilonewton meters plus or minus using a safety factor of 2. And the data given in the figure below, figure 3, this one here, we have to determine a suitable diameter for the shaft. Okay, now this is quite interesting. We want to design a shaft for infinite fatigue life. Okay, so we know that this shaft, let me draw it. We have a shaft we have some pulleys at the end. And it says this is being symmetrically supported, something like that. What did it say? Supported symmetrically in between two bearing housings. So that means that this should be a bit longer. We continue a little bit. Here and here, here and here. Because this is where we have the bearings. Okay, so this is supported in this way. And these are the pulleys that, of course, will have some, there is a belt here. There is a belt here. And they are under some forces here and here. We don't care about the forces. We know that it will be under the forces. And this, of course, as this rotates, the bending moment, which is always applied in the same direction, it's applied in the same direction for us, that we are outside of the system. But if we were sitting on the shaft, we would see this bending moment rotating. Do you agree? So if I follow this point is now up, but then at some point, this will be down. And so that means he will feel tension and compression, tension and compression, tension and compression as it rotates. And so we have an alternating bending moment of M plus or minus 1.2 kilonewton meters. Was it 1.2 or 12 point, whatever? 1.2? Yes, 1.2 kilonewton meters. We want to find what is the shaft, what is the diameter of this thing for infinite fatigue life. And we don't have anything else. Look, that's the only bit of information we are given is this one and this picture here. Let's say it says mild steel. So we have two curves here. One of which is for mild steel. Let me zoom in a bit larger. One of these curves is for mild steel, which is this one with the squares, which are circles apparently. And these axes are for the aluminum alloy. So of course we are looking at this curve here and not the other one. And this curve has, as you can see, a specific endurance limit. What is the endurance stress of this curve? So what is the stress below which I'm always 100% safe? Say again? 190. Yeah, that looks like it. See, this is 200, and this is a bit lower than, yeah, 180, 190. Well, in this case, I would say 190 because see, this is 150. So it looks closer to 190 than to 180, but it's fine. Even if you had used 180, it would not have been a mistake. Okay, that's fine. So let's take 190. So we have that sigma E from this 190 megapascals, and this is from experimental data, so from the curves. Okay, now we must be below this stress. Do you agree? Okay, so let's be below. So in order to have infinite fatigue life, we need to stay below sigma E. And so that means that whatever stress, so using the Flexure formula, whatever stress we get at the most critical point, let's call this point P, and so let's call it sigma P. Whatever stress we get at point P, which is equal to m over I times y, and y in this case is the diameter divided by 2. And how much is I? This is a circular shaft, of course. So remember that I for a circular shaft is pi d to the power of 4 divided by 64. So this stress must be smaller than sigma E. And so I can just look at the second part of this equation and say that 64 m over pi d to the power of 4 times d divided by 2, smaller than sigma E. And so this d and d can go away. This and this can go away. So this becomes 3. And this 64 and 2 can go away. This becomes 32. And so I get that 32 m over pi d cubed smaller than sigma E. And so this corresponds to d cubed greater than 32 m over pi sigma E. You agree with me? Can you see why I went from smaller than to greater than? Because I'm looking at the equation from the other side. Okay, can you see it? Good. And so I can just say that d must be greater than the cubic root of 32m over pi times e. And this is just a number. That number is, lo and behold, 50.48 millimeters. Must be greater than 50.48 millimeters. And this is what we need. D must be greater than 50 millimeters. See, if you make it smaller than 50 millimeters, it might resist to yielding, but it will not resist in fatigue. At some point, it will break. See, even if you made it statically sound, statically safe, it will still fail at some point during its operation. Any questions? Again, as you can see, very easy. See, this is just, I think that's the easiest part. If you can figure out what quantities are involved. Safety factor, does it say safety factor? In this case, it's safety factor of 1. So this 50.48 is for safety factor of 1. If you make it 50.4, James pointed out is safety factor 2. Where is it? Oh, it says here, using a safety factor of 2. Oops, my fault here. That means, thank you. So remember that we have another piece of information, safety factor. Safety factor must be 2. And if the safety factor must be 2, that means that this must be smaller than sigma e divided by the safety factor, basically. So this is divided by the safety factor. And so this becomes safety factor that goes here. But since I copied it from the solution, I believe that this is still the correct number because I haven't done this calculation. Do you agree? Probably I'm missing the safety factor also in this other part. So this goes here, SF, and this goes here. SF. Very good. All right. Okay. So let's get rid of this fatigue 1. Let's go to fatigue 2. Fatigue 2 contains Miner's rule, basically. Remember the fractional damage or the linear accumulation theory, damage accumulation. And I'll show you, especially question 3 is particularly nice. So let's start with question 2. For question 2, we have the values of the endurance limits at various stress amplitude levels for a low alloy construction steel specimen are as follows. So what you have is that you have a table. So instead of having a curve, now in this case, you have the same information in a table. This is Waller's curve in form of table. So let me write it here. You have Waller's curve in table 4. So we have another specimen completely independent from the first one, which is subjected to a program of cycles at different stress amplitudes as follows. So this goes 3000 cycles. This goes, I'll create another table. So we have 3000 cycles at 450 mega, at 510 sigma amplitude, 510. And then we have 12,000 cycles at 450. And then we have 80,000 cycles at 380. And we know that this remains unbroken. After all these cycles at different stress levels, this is still hasn't failed. So how many additional cycles this can withstand at 480 megapascal? And we assume 0 mean stress conditions, so we don't have to everything is just purely stress amplitude. So this is what I created here. I created a small table. So this is my unknown, X. These are the number of cycles, effective cycles. This is in megapascals. And then I have NF that I can find from the Waller's curve. This is also in cycles. From Waller's curve, I find this. And we have 510 corresponded to 10,050 cycles. $450 corresponded to 50,500 cycles. Uh, 380 corresponded to 270,000 275, well, that's odd thing. I think it's 275,000. 275,000. And at 480, this one, 20,800. Okay, now that I have this information, and let's say that these are condition one, sorry, first operation, second operation, third operation, last operation, because we know that it breaks now, then broken. We can find X. How do we find X? Well, remember Palmgren miners. So Palmgren miners rule. Well, linear accumulation of damage. That means that the damage, the total damage in percentage, is the sum of Ni over Ni, capital Ni. So you have effective cycles over cycles to failure at that particular stress. So we can just do this divided by this, plus this divided by this, plus this divided by this, plus this divided by this. We know that it's broken, so it must be equal to 100%, basically. So again, two ways of doing this. You either expand this to say N1 over capital N1 plus N2 over capital N2 plus N3 over capital N3 plus X over capital N4 equals to 1. And so you find X because everything else is given. And so you can say that X equals N1 over capital N1. So 1 minus this plus N2, N2 plus N3, N3, and this is times N4. This is, it's everything times N4. With something like this. Or you can also find how much damage has been accumulated in the first 3 runs and see how much remaining life you have. But it's the same thing. It's just rearranging the equation. We are doing exactly the same thing. But in that case, we also estimate how much percentage life we have left. Instead of doing it in one go, you have this many cycles left. Because this X, first of all, this X should be 3598 cycles. Okay. Or, as I was saying, or you do N1 divided by capital N1 plus N2 divided by capital N2 plus N3 divided by capital N3 equals how much? Well, we can check. Do this in a calculator. And we have, not here, this goes up, this goes here. So 3,000 over 10,050 plus 12,000 over 55 plus 80,000 over 275,000. Okay, this gives 29%. Does it? No, what am I doing? I don't trust a calculator in Windows. So let me do this very briefly in Wolfram alpha. This would be 3000 over 10050 plus 12,000 over 500 plus 80,000 over 275,000, and this is equal to. So you have 82% of the life spent 82.7%. Okay. So we get this information here that this component has spent 82.7% of its life. So the remaining life, which is of course 100 minus 82.7, is equal to a 17.3. And that's also equal to x over m4. Okay, so you can just solve x equals 0.173 times m4, which is equal to, again, 3, 5. That's another way of doing it. Now, at the exam, I might ask you just number of cycles, or I might ask you what is the life spent, how much life this component has spent, and so you just use one approach or the other, but it's the same equation. That's what we're doing. See, this 1 minus thing was done here instead of here already in the bracket, but it's effectively exactly what we did. Okay, so let's do question 3 and let's go home. So question 3, and look, this is the fact that I was saying to Effia earlier is that you can use whatever units you want. The fact that you have fractional damage is a non-dimensional quantity, okay? So it doesn't have to do with stress at all. It can have to do with anything. In this case, let me close this instrument of the devil. In this case, we have the safe operation of a military aircraft in terms of fatigue life depends on the type of service for which it is used. One particular type of aircraft has a rated life of 1,600 or 2,000 hours when used for combat training or surveillance missions, respectively. Now you have, see, this rated life. If you use this aircraft for 1,000 hours of combat, okay, where is it? No, yeah, combat, training, surveillance. Okay, so training is apparently more training than combat. I wouldn't have said so, but apparently we have 1,000 hours for combat, 600 hours live for training, and 2,000 hours for surveillance operations. We have one of these specimens that has seen 50 hours of combat, 300 hours of training, and 400 hours of surveillance. And we have another one that has done another history. And we can ask ourselves how many hours of training service we may have each aircraft be used for before we send them in for maintenance. Also, we know that we have two missions. One is a combat mission, one is a surveillance mission, each of which is 200 hours that must be completed. Which aircraft do you send where? Okay, so you have these two aircrafts that have these histories. You can look at them from the logs. So you have to decide, as the military engineer, you have to decide which aircraft should be assigned to which mission. And when it returns, how much life is left in these aircrafts once they have returned, hopefully, from their mission. See, it doesn't have to do with stress at all. It's just hours in service. You can answer these kind of questions quite easily. So remember Miner's rule. that's D should be smaller or equal than the sum of Ni over capital Ni. That's for the damage to remain small. So D is equal to, sorry, this is D is equal to this, but this means smaller or equal to 1 for some life left. And then let's create a table. We have a table with our experiments that we know that we have 1,000, 600, and 2,000. So NF would be 1,000, 600, and 2,000. And these are the operations. And then we have combat, training, surveillance. So let's check. This is the this is our Waller's curve. These are experimental values. And these are well, this is type, this is hours. Always put the units. Okay, always put the units. This is NF, not NT, which is basically the cycles to failure, which is not in cycles anymore, it's in hours. And then we have aircraft 1 and aircraft 2. We can generate the logs of these two aircrafts to see what have they done in their lives. Aircraft 1 has done 50 hours of combat, 300 hours of, let me write it down, 50 hours of combat. So it's 50, so hours. And this is operation. It's 50 hours of combat. And where is it? 300 hours of training and 400 hours of surveillance. 300 hours of training and 400 hours of surveillance. Okay, so this is the log for aircraft 1. Now we have another log for aircraft 2. We have hours and operation. For aircraft 2, its log is about combat, so CTS, exactly in the same order, and they are 500, 150, and 300. So 500, 150, and 300. Let me triple check. 500, 150, 300, okay, and this is CTS. So CTS. So these are the logs of the aircrafts. Now we can answer our questions. Question A, how many hours of training each aircraft has got? So how much more training so X and Y would be my unknowns. And so X would be equal to 50. So this is, see, the number of hours, effective number of hours, and these are the numbers of hours to failure for combat. So 50 over 1,000 plus, so that's not X. So let me do all the equation first, and then let me rearrange it. So it's 50 over 1,000 plus 300 over 600 plus 400 over 2,000 plus X over T is 600 equal to 1. This is my equation from Miner's rule. And here it's the same thing. Here I have 500 over 1000 plus 150 over 600 plus 300 over 2000 plus y over t 600 equals to 1. See, I have my only unknowns here are x and y. So from here I can find x equals and y equals. And x should be equal to 150 and y is 60. 150. And as you can see, since we have used hours, and I forgot the other number, 60. Done. Very easy. And much ingenuity to be used for these kind of questions. Now we have combat and surveillance of 200 hours each. Now, which aircraft should we be sending on each mission? So let's check how many more these are training hours. Okay, so these are the training hours left in each plane. But how many combat hours we have left? It's just exactly the same thing. Imagine this. You have, we have combat and surveillance. So we can find X, so let's call this XT and YT. So we can find XC and XS, YC and YS. So these are the hours of combat left and the hours of surveillance left for each of the two aircrafts. And I mean, guys, don't let me do this all over again. It's just exactly the same, but you have to change XT with XC, and this 600, which was corresponding to T, you change it with 1000 here in order to get the other equation. So everything is the same, but this last term, let me highlight this in green. This last term is XC over 1000. That's the only change. And in this equation, this term is XS over 2000. And exactly the same change would be for the other one. Turn this off. It's so let's go here, and we get where we have aircraft 1 for combat and aircraft 2 for surveillance. Can you do these calculations for me, please? So let me write the equation for the first one. This would be 1 minus 50 over 1000 plus 300 over 600 plus 400 over 2000 times XC was 1000 and this is XS, which is equal to this times 2000. So yeah, 2000. So how much are these numbers? $500, 150, 300. And this one is No, this time. And this is 1000. Okay. So can you tell me about these numbers? How much are they? Anyone? Let's check the solutions. Let's check the solutions. Fatigue 2. Is these ones. Question 3. Question 3, for combat, we have aircraft 1, 250 and 100. So this is 250 hours. This is 100 hours. And let's see, put this down here. Oops. And the other one is 200 hours left. For combat, for surveillance. Aircraft 2 is 200 hours, of course. And this is 500, of course, because it's the same, it's just twice as much. Okay, so as you can see, for combat, it's a 200 hours combat mission. So we can't send aircraft 2 into combat because it only has 100 hours left of combat. So we must send aircraft 1 over to combat, and it will come back with 50 hours left. Whereas if we send aircraft 2 to surveillance, that is 200 hours, which is exactly 200 hours. So it will barely have any life left when it returns. Okay, so send aircraft 1 to combat, 50 hours left. Upon return, then send A2 to surveillance, and would be no life left upon return. Done. Any questions? As promised, it's 3. And I took my sweet time as well. So as you can see, this is very, very simple, all very simple. If you don't have any more questions, let me just, I think I'll stop recording now.